Hello, and thank you all very much for joining us today for our talk, Hardening Secure Boot on Embedded Devices for Hostile Environments. So, together, the three of us, Cristofaro, Niek, and I, have a lot of experience breaking secure boots, analyzing secure boots, evaluating secure boots. And also, when we look at the public talks, things people have done in public, we see, for instance, that Bunny, who gave the previous talk, talked about hacking the Xbox in 2003. And 2 hours ago, we had the latest installment of Breaking Secure Boot from the CTS Labs guys. So after all that time, secure boot is still often vulnerable. So therefore, our goal is to try and create a secure boot guidance for people designing secure boot, so designing the hardware, designing the software of secure boot, people actually creating this hardware, people actually writing this code, and people who then actually have to take all that work and put it into a finished product. So in the next couple of months, we'll try to release a white paper, which we're still working on, which will hopefully give quite a bit of guidance there. However, in this presentation, we'll try to take a little bit of an offensive focus. So we'll show some known attacks and some new attacks. And using those new attacks, we'll try to give some new perspectives in attacking secure boot, but also in ways to defend it. So, I will give the introduction, I will talk a little bit about secure boot, and then Cristofaro and I will talk about some attacks and some mitigations. And then Niek, who's behind me, will give a demonstration, a live demonstration, which he's still trying to fix, I think, followed by a wrap-up. Okay, so let's imagine a system, an embedded system without secure boot. So basically there's a system on a chip inside one package. It has a processor, it has some memory, it has some code, and attached to this package is a piece of flash memory containing some code, and there's a DDR chip. So this is the state when the device is turned off, and when it boots, when it's released from reset, the ROM code will load the BL1 into SRAM. And then the BL1 will initialize DDR and load the BL2 into it. And so on and so forth. Okay, so as we already saw, this leads us to some attacks. So there are two major attacker scenarios, and that is one, a hardware attacker desolders this flash chip, reprograms it, and solders it back on, or an attacker with software control basically reprograms flash. So that's why we need secure boot. So what is secure boot? And, well, luckily today we already had an explanation from the CTS Labs guys on what secure boot is. But just to recap, it's basically the authentication of loaded images, and it has a root of trust embedded in hardware. And for us, that means that immutable code and data are stored in ROM and OTP, so one-time programmable memory. So now let's try to explain secure boot. So here is the picture we saw before. The ROM has copied BL1 into SRAM, but now there are also signatures. So the ROM will first calculate a hash of the BL1, and then verify it against the reference signature. So either an RSA signature, or as we saw with the PSP, maybe just a hash that is stored somewhere. And basically, if these signatures match, you boot, and otherwise, you don't boot. Okay, so that's an easy explanation, but you know, the real world is typically a little bit more complex. So on an embedded device, a typical secure boot flow can look something like this. On one end of the spectrum, you have hardware and ROM, and at the very other end of the spectrum, you actually have applications. And as you go from one end of the spectrum to the other end, some properties change. So first of all, a lot of privileges are dropped. And we don't mean just, hypervisor mode, kernel mode, user mode, also things like access to cryptographic keys, access to the ROM code itself, and maybe access to engines are dropped or change. Another big difference is that hardware cannot really be updated in the field, and neither can ROM code, while at the other end of the spectrum, the applications might actually be updated multiple times a day. And the last big difference is that there are actually a lot of manufacturers involved. So in this hardware and ROM stage, basically that's the responsibility of one manufacturer. But within that company, maybe another group is actually responsible for writing the bootloader. Then a third party may be responsible for actually providing the TE OS, and then an original equipment manufacturer is actually responsible for basically the normal world bootloader and maybe something like a Linux OS. So there are actually a lot of different interests in a secure boot chain. And all of these parties and all of these interests all have a slightly different perspective on secure boot. Okay, so the goal of secure boot is to mitigate a number of threats. So it's basically to prevent modification of code and data in Flash. It's to allow you to actually have secure updates. And it prevents attackers from creating persistent footholds. And it also prevents access to assets like keys, code, and crypto engines. And finally, it's an important part of preventing attacks from escalating, for instance, from the RE to the TE. Okay, so when we talk about this attack surface, we believe that basically you either have a broken design or a broken implementation. And this basically translates to, as well, also translates to maybe actually having broken software or actually having broken hardware. So I'll now give some examples of secure boots having been publicly broken. But again, the CTS Labs guys did an excellent job this morning of actually giving us another examples, so please also take that one in mind. Okay, so our personal favorite of a secure boot ROM bypass is the AM logic. So we believe it to be a broken software design that is available because of weak cryptographic options. And the bypass is basically a downgrade attack from an RSA signature to a SHA signature. And as the SHA signature contains no secrets, an attacker can just modify the code, update the hash, and that's it. So how could this have been mitigated? Well, first of all, they probably shouldn't have supported weak cryptographic options. And in general, we suggest that limiting the amount of options an attacker can choose from is good for security, because an attacker will always choose the weakest option. Our second example is a Nintendo Switch boot ROM vulnerability, and we believe this to be a software issue that was basically due to a broken implementation. And it's basically a classic buffer overflow attack. So in the USB recovery mode, there's this buffer overflow attack, which can actually just be, exploited using normal software exploitation techniques. So how could they have mitigated this? Well, they could have just written secure software. So I got complaints. Sadly, that's not an acceptable answer. So they should have tried to make software exploitation harder. So they could have used, for instance, typical mitigations like stack cookies, ASLR, CFI. They could have used memory protections to enforce write, XOR, execute. They could have used, MPUs, MMUs, IOMMUs. So in 2019, I'm standing on stage at a security conference, and I'm talking about, implementing stack cookies, ASLR, and CFI. That sounds a bit stupid, but you have to remember that most secure boot implementations implement none of these mitigations. Okay, so I said you could write secure software. Now, even if you write secure software, you might still have broken hardware. So our next example is fault injection on the Nintendo Switch. And basically, they skipped the hash verification stage using voltage fault injection. So what is fault injection? Well, basically, you try to make glitches using, let's say, an electromagnetic pulse, a laser, playing with a target's clock or power, and you try to introduce a glitch. You try to get that glitch to introduce a fault in that device. And typically, we can model these faults as, let's say, something like instruction skipping. So pretending that this fault will skip an instruction. So, for instance, in the hash bypass case, perhaps the branch instruction was skipped. We have also another model called instruction and data corruption. And basically, this means that perhaps when the instructions are being fetched from memory, one of the bits falls over. And instead of executing the original instruction, you're now executing an entirely different instruction. Cristofaro will talk a little bit more about that later. So the key takeaway here is that fault injection alters the intended behavior of both hardware and software. So, how could we mitigate this? Well, I'll now give some software examples. So perhaps we could add some redundancy. So instead of checking that hash value once, you check it twice. And then only if both checks match, do you actually boot. You could also add random delays. And basically adding random delays makes it harder to pinpoint the exact moments in time when you need to introduce a glitch. And especially when you combine this with something like double checks, it makes it that much harder to actually bypass that check. You could also add some countermeasures in hardware. For instance, you could, again, add redundancy. Perhaps you could use a lot of checksums on things. Perhaps you could add glitch detectors. So actually, for instance, adding light sensors to detect that someone is shining a laser on your die. Or perhaps measure the voltage to ensure no one's playing with it. And finally, you can also add non-constant timing, for instance, using clock randomization. And again, this makes it harder to pinpoint the exact moment in time the glitch needs to be introduced. Okay, so this is my final example. And it's basically a fault injection attack on the PS Vita. So we believe that it's basically a broken implementation on broken hardware. And again, using fault injection. So in this case, what they did is they used fault injection to bypass a length check. And that means now more data is copied in, which again gives you this classic buffer overflow attack. So how could you mitigate this? Well, it's fault injection, so you can use all these fault injection mitigations. But on the other hand, it's a software exploit, so you could use all these exploit mitigations. So I think at this point we've realized that designing secure boots is not simple. It's not easy. But we also have to take into account all these other constraints. So we need to initialize hardware as well. We need to be aware of performance constraints. We need to keep engineering costs low. And we may need to recover devices in the field. And additionally, sometimes customers have, extra requests as well. But we believe it is very important to get it right, because bad security can be very expensive. So, for instance, if you need another tape out, that can cost upwards of $1 million. And that's before you take into consideration the extra damage you might have from the bad publicity, or the fact that you have unsold inventory, or inventory you'll have to sell for a lower price. On top of which, you'll probably still need to pay this additional engineering time. Okay, with that in mind, I now discussed some public attacks, and Cristofaro will now talk about some new attacks which the world has not seen yet.
Okay, thank you, Albert, for this nice overview on current attacks, which are let's say, up to date at the moment. But it's important to realize that the attack surface here can be much larger than it's usually discussed and intended. So we've tried to push the boundary a bit more and to discuss a few attacks which we think have not been discussed before, or even presented, or even demonstrated before. We're going to share with you something which I think is quite new and shared for the first time. So the first one that I would like to discuss is fault injection on OTP transfer. There is one thing which all the attacks that Albert shared that they do have in common. So all the attacks occur while the code is actually being executed. So there is always the CPU executing instructions which are attacked in one way or another, either through software bugs or fault injection attacks, in order to alter the flow and the execution, intended execution of a secure boot. But we are proposing here a different attack, which is attacking the secure boot before any code is actually executed at all. Let's have a look a bit more in details to this attack. So there is one important chip component which is heavily used in embedded devices, although not necessarily in common PC architecture, which is OTP memory, which stands for one-time programmable. It is what is being also commonly referred to as e-fuses, also Bunny mentioned in his talk. So the idea is that OTP is an ideal storage for configuration data. You have to imagine that, for example, here you have flags that might say if your secure boot is enabled, or if the stage needs to be decrypted before being verified, and things like that. Why this is an ideal storage? Because it's one-time programmable, meaning that you can actually change the physical properties of the cells that represent the bit. You can change at 0 to 1, but you cannot reset that to 0. So that is permanently set, let's say modulo some, say fib attacks, for example. That is permanently set to 1. And this can happen anytime in the device lifetime. Basically, even in the field, you can enable secure boot, and if you do in this way, unless you bypass it, then there is no way that you can disable the secure boot anymore, because that flag has been enabled in the OTP memory. So the main consumer of this data, of this information, is actually the ROM code that takes decisions according to the information which is stored. You can see here an example where number 4, calculate hash, and 5, verify image. So dash verification, dash calculation, the image verification is only performed if the bit 17 in the OTP shadow location is set to 1. So this means that there is information which is stored, which allows to perform the signature verification. It is a memory mapped location, otherwise we will not be able to dereference that pointer, basically. So this means that there is a register which is memory mapped at runtime, which allows you to query this information and act upon. But it's a register, so this means that when the SOC is restarted, that register is typically a 0 value, is cleared. So when the CPU is executing this code, someone has to populate, or has already populated that register with the value stored in OTP. And this is what we call OTP transfer. It's a mechanism that populates registers, shadow registers, with information from OTP. So this transfer is performed in hardware. There is hardware logic performing it before the CPU is actually released from reset, and then any ROM code is executed, for example. What it's important to realize this is that this hardware stage happens before the CPU is even started. There are multiple resets point in time in an actual system. So when the SOC, the system on chip, or the system starts, is released from reset, then there is hardware logic which performs initialization task. And only once the proper initialization tasks are completed, then the CPU is released from reset and starts executing code, fetching instruction from the designed location. So that part, hardware OTP transfer, happens between a very large time window when you press start, reset, basically, and when the actual CPU is started. So let's have a look at what happens there, basically. So we have a typical OTP chip here. which is divided in banks, which is then organized in cells, and these cells are the one that you can set from a 0 to 1. So there is a special OTP hardware block, which is just data. And of course, you need something that transfers this data to proper location, which is an OTP controller. Usually connected to the OTP main chip with a bus which can transfer between 8 and 16 bits, which can be quite slow, so a narrow bandwidth, and where a common response protocol actually queries the logic on the main chip in order to transfer data. So you have to imagine that our flag that says secure boot is enabled travels from the main chip, main component from OTP, on the bus until it rises to the OTP controller. Then the OTP controller, depending on the data which has been fetched, basically, typically serially from the main chip, actually transfer this data to the intended hardware, including the shadow register. Keep in mind that there might be additional hardware which might use OTP configuration, and the OTP controller has the task of transferring properly this information. And this information may not be accessible to the CPU at all. And the CPU has not started yet here, but once the information is in the shadow register, then the CPU can be released from reset and can access the information over the main bus via the memory mapped mechanism that we're seeing. So let's keep in mind that fault injection can alter the behavior of the chip, not only software, but also hardware. So with this in mind, let's see where we can attack. In principle, while the bytes are being transferred, so let's assume that you have a 1, which is set for secure boot enabled in the OTP main. If you properly time your attack, you might be able to toggle that bit from 1 to 0 while it's being transferred to the OTP controller, or change it while it's being processed on the OTP controller, or even while this is transferred to the shadow register. Keep in mind that the attacks have different opportunities because the bus have different speeds, different bandwidths, of course, and even information might be transferred either serially in an initial stage or parallel. So it's just a matter of understanding that even before the CPU is started, you might have an option for changing this configuration in the end. So basically, we can affect the signature verification and the stage encryption by bypassing the secure boot and also the encrypted secure boot, depending if you're able to toggle only one bit or both with one or multiple glitches. Keep in mind why this is important, why I'm saying one glitch. Because the transfer happens byte level, when the information might be bit level. So in that single byte, you might be able to have both the information regarding the signature verification and the encrypted secure boot. So basically, this is what we think is doable. In our experience, we know it's doable. We are not doing a demonstration on stage on this point, but we're going to share another one which we think is important. A fault injection encrypted secure boot without actually having an encryption key. Let's see how this is possible. So this is the signature verification, and the verify there is the cornerstone on every secure boot. You have to relate, for example, to the PSP verifying the next stage. It might be an HMAC comparison, for example, or it may be an RSA verification, but regardless, there is always a verification point, and there is always a conditional that says you should go here or you should go there. Okay. One of the important fault models, first, what is a fault model? A fault model describes the effects that a fault can have actually on a system. One of the most common fault models is called instruction skipping. It assumes that you can cause instruction not to be executed, such as if you introduce a fault at the right time, you might have that the instruction which is being executed at that point in time is actually skipped. Actually, we know this is inaccurate. So from a physics point of view and from a computing system point of view, we really know it's inaccurate, because it's very likely that instructions are actually modified or corrupted while, for example, they are being fetched from the memory towards the main CPU. This is inaccurate, but it's sufficient because it models the behavior of the chip. So it's actually a behavioring model rather than an accurate physics model of what happens. This is sufficient, so to the point it has been widely adopted both by academia and the industry. So most of the fault injection attacks that you are going to describe or to see described in papers relies on the assumption that you can change data while it's being stored for DFA, or that you can skip an instruction. So even if it's inaccurate, this can be useful for affecting the code flow. So let's try to see how this can be used for bypassing secure boot. So the textbook attack is the following. You have your bootloader BL1. When the device is turned off, you just reflash in software or in hardware. Sorry, by software or hardware means. And replace that with a malicious image, basically, which is your payload, okay? Which in principle should not be accepted because the signature is actually wrong. So that verify is going to bail out, says, hey, I don't want it. But the point is that if you are able to time that comparison, that if, you might be able to, at the assembly level, you might be able to skip the call to that function. You might be able to skip the assignment to flags, for example, to test registers. You might be able to skip the decision point and fall through, because that's what you might be doing. So if you're able to skip that function call, then you will be just going to jump and execute in the malicious image. This might be, for example, say a way of bypassing also the PSP secure boot by targeting either the HMAC comparison, there is an if, likely, or targeting the comparison of the hash stored in a signature, depending on the R. So again, props to the guys from CTS Labs. So the point is that glitch at the right moment and profit. But there is a big problem here, because if BL1 is encrypted, then you have an encrypted secure boot. Do you think this can be applied? Well, actually, there is a big problem, and we're going to see that in a moment. Because there is first a decrypt of the image in memory, and then the signature is checked. This is a quite typical approach from a device manufacturer, and the reason is that you're allowed to have one single signed image, which can then be encrypted with device encrypted specific keys. If you do the other way around, you would need to first encrypt and then sign, and add a signature different for each device. In doing this way, you first sign the image, then you encrypt it, and when you actually are booting that, you first decrypt, and then you verify the signature. So there is the additional step here at level 2, which brings up a lot of problems for applying the previous attack. Because you remember that we are putting our malicious image in plain text in the flash. The problem is that you don't have a key now that would pass the decryption stage. So whatever you put in plain text is going to decrypt it to garbage. And if you are going to bypass the signal verification, your code execution is actually going haywire, because you don't control the code which has been decrypted, because you don't have the key. And that's the reason why usually FI-only attacks, so attacks which only rely on fault injection, are considered infeasible when targeting encrypted secure boot, to the point that it is often suggested as a countermeasure. Encrypt your secure boot, and then the attacker will need first to retrieve the key and then perform the fault injection. We are going to show that that is a misconception. In order to do that, we are going to consider a different fault injection model, which is instruction corruption. So before, we assumed that a fault could only skip instruction. Now let's assume that the fault can actually alter, modify, corrupt instruction in a way that might be useful for an attacker. So you know that the instruction has the operands where the destination register are specified. Okay? So imagine that you are copying some data from the memory or from flash or from RAM and put that into a register, like load this information, these 32 bits, into a register. The point is that if you might be able to change that register by injecting a glitch. And we'll see in a moment how this could be leveraged. It's a fairly new application of this kind of fault model. It has been discussed first in 2016, Niek, Albert, and Mark Wittmann. And we are going to use this for modifying code and getting runtime control. Different from before, where we altered the existing code flow, now we are good really to get control. So let's see a bit the attack in detail here. Again, the device turned off. Before, we placed the plain text image in BL1. Okay? Now we are going to place still the same image, the payload, with a tail of pointers, a pointer sled. A pointer to what? Well, we know that that code is going to be placed in SRAM at some specific address. Let's assume that you know that address, okay? What you have to do is that sled of pointers has to be exactly that address. So if that goes into SRAM at address 10, for example, is going to be loaded at address 10, then your pointer should be just a sled of 10, 0x10, okay? And the point is that this is copied in sequence. You start from the first and then go to up to the end of the image. If you glitch during the pointers, while the pointers are being copied, something interesting can happen. So if you glitch during that mem copy that copies the image, something really nice can happen, because you can assign the value that you are copying, so the pointers, to a different register. And if you are in an architecture that allows direct addressing of the program counter, like ARM32, for example, which is exactly like the PSP that we discussed before, at least that's what it looked like from the assembly, then you could assign that pointer, which is being copied into a register, directly to the program counter. And we all know what happens when the program counter is set to a value, meaning that the execution flow just immediately goes to that address, correct? And what is that at the address? It's the start of the image in SRAM, which is our code. So this means that if we glitch during that copy, while the pointers are being copied, the pointers may end up in PC, and basically we start executing our code flow. And what about decryption and signal verification? Well, they're gone, because the control flow is ejected during the copy. So whatever software has been written there, whatever countermeasure has been written there, double checks and randomization and all these things, is actually gone. So we are bypassing in one go the decryption and the verification, which happens after that mem copy. So basically what we are doing here is that we turn an encrypted secure boot into a plain text unprotected boot with a single glitch, and for which we don't need a key, because the image we're placing there is going to be in plain text. You're going to see these now in a few moments. You might hear some beep, perhaps the one on the front rows. Pay attention to this, because the system with this attack is going to be bound in a very interesting way. Well, first, the timing is not so relevant, because your sled can be even quite long. So you don't have now to pinpoint one signature verification. You just have to take the right glitch while multiple pointers are copied, okay? So the timing is not so much a problem. So your trigger can be really imprecise. You get full PC control. Why? Because you are diverting the data that you have in flash, that you control, to the wrong register. So you can actually say to the PC, go here, go here, go here, go there. And you don't need a software vulnerability for that. So even if your software is perfect and your hardware is sensitive to fault injection, you can actually also do that. One important point, the technique we're discussing here does not depend on how you inject the glitch or cause the fault. It's irrelevant. You can do that with voltage. You can do that with laser, with EM. In principle, if you are able to do that also with raw hammer, although it's extremely difficult to do that during boot. But in principle, the technique would be used in the same way. By the way, we used also this technique last year in order to escalate our privilege from users to root and to kernel, to get kernel code execution on a fully patched system without any software vulnerability. So the fault model we are discussing here is extremely powerful because it bypasses any software which happens before. So whatever is implemented as a countermeasure afterwards doesn't really count. Well, on this I leave the stage to Niek, which is going to show how is this possible, if the attack is practical or viable. Thank you, Niek.
Thank you, Cristofaro. So before we start, I would like to make one small disclaimer, is that what we are targeting here on stage is not actually real-world code. So there's 2 stages that are programmed by us, and it's for demonstration purposes. But before we go to the other laptop, let's have a look at what we're having here laying in front of us. So we have the most important device, which is actually capable of injecting the glitches into the target. And in this case, we use the Risker Spider, which is really a Swiss knife for doing fault injection attacks. But nothing prevents you from using easier to access tooling like Collins Chip Whisperer, for example. So we communicate with this device using a laptop, where we have a Python framework that allows us to control the hardware. And this laptop is also used to communicate with the target through the serial interface. And in this case, we're using an STM32 chip, which is ARM32. And actually, these type of chips are also used for products like crypto wallets, for example. So even though our product is a knife, we don't even use too many things. We provide an arbitrary voltage signal to the target. That's fundamental. So what we need to do to the target is we need to somehow remove the original power supply. And with the power supply, I don't mean the power provided to the board, but actually the power that's powering the ARM core. So that's typically a VCC signal. In this case, for this particular target, it's roughly 3 volts that we use. But also, because we are targeting secure boot, we need to reset the device every time in order to trigger the secure boot. So we're also using a system reset in order to reset the device every time with the GPIO pin. But everybody knows that does some hardware hacking, that even when you have a simple setup, that the cables will grow everywhere. But this is exactly what we have laying in front of us. I do not have the time to explain what all the cables are doing, but please come to us after the presentation, and I think we will build down the setup during one of the breaks so we can talk about it in more detail. So what we did in order to make this attack is that we first programmed a secure boot implementation. And basically what is happening here is the device gets reset, some hardware gets initialized, then BL1 is executed, and BL1 is actually loading, decrypting, and then authenticating BL2. So the binary data that you see there is actually a copy of the BL2. So as you can see, it's completely encrypted due to the high entropy. So what we did is we modified the BL2 in a similar fashion as Cristofaro explained. So on the right side, you see the BL2 again. And whenever it starts up, it will be loaded by BL1. It will still be decrypted, but it will be decrypted into garbage because we do not have the key. And then the authentication of BL2 will actually fail. But what you can see is that we loaded a few things in there. So first some knobs, these are not too relevant, and then actually our payload. And as you can see, on the right side there's a string, and that's already a giveaway of what's going to happen. And after this code is actually the pointers that Cristofaro mentioned. And these pointers don't point to the flash, but they actually point to the buffer in SRAM where this image will be copied. So whenever we boot the device with a valid image, there will be some strings printed on the serial interface. So you see it started BL1, then it's loading BL2, decrypting BL2, authenticating BL2, and then it jumps to BL2, and then BL2 happily says, I also started. But for the malicious image, BL1 still starts, it still loads BL2, it decrypts BL2, but you'll see that afterwards it stops, because like I said, the authentication of BL1 will actually fail. And this is exactly what we will try to bypass using fault injection in a similar fashion as Cristofaro already explained. So we can switch to the other laptop. Can I have the other feed?
Let's switch to the demo.
Thank you very much. So here on the left side, let's focus on that first. We see actually a signal. And this is a signal measured by the oscilloscope. And this is actually the system reset that we use to get the board out of reset. So every time the signal goes up, the system is actually released and the hardware starts initializing. So I can open another signal. This other signal is actually the voltage provided to the target. And as you can see, I lied, it is not around 3 volts, it's actually around 2 volts. But it's enough for the chip to operate. And roughly in the middle, you see sometimes this red dip in the signal. And that's exactly the glitch we are injecting. And of course, we know roughly where to inject this glitch. Because in principle, when you start doing fault injection, the attack window starts from the moment the chip goes out of reset until the moment you can detect something goes wrong. But we already roughly know this location. So let's look at the right side, which is our interface to control the hardware. I will just briefly stop the updating. So what you can see is that we roughly performed since the start of this presentation 9,000 experiments. We randomized the glitch delay a little bit, so we go from column from left to right. And then the glitch voltage is the amplitude of the dip, and the glitch length is the width of that dip. And then on the right side you see that the expected data is being returned by the target. It's finalized with stopping, so the target detects that it actually cannot authenticate the image. Now, when I start it again, you'll see that there's different stuff going on. For example, this purple one, it's a bit hard to read, but what's happening here is that actually a CPU exception is thrown. So somehow the CPU got a hiccup, and it printed some information about the current state of some of the registers. But for the people that actually heard the beep, every time you heard a beep, something else happened. And we have a look at this red experiment, and we see still that BL1 is successfully started, but then directly afterwards, it does not print the expected strings anymore. We directly jump to our payload. So somehow we trick the CPU into executing a different instruction that resulted into loading one of the pointers that was in our flash into the PC. So I can show you that since the beginning of the presentation, we bypassed this secure boot implementation roughly 260 times in roughly an hour. So that's pretty stable for this particular implementation. Can I go back to the other screen again? So we showed multiple ways of bypassing secure boot, whether it was done during software exploitation or a hardware attack like fault injection or a combination of. Well, our talk was hardening secure boot for hostile environments, and so far we only explained the offensive part. But the defensive part will really be explained in more detail in our paper that will be hopefully released early this year. But to give you an idea of the things that are being discussed, some of these things are open doors, but very important. For example, you want to make sure that your implementation is, or your design is simple. The more complexity you add, the more opportunity, or the more opportunity there is for mistakes to slip in, or more opportunities for attackers. And in similar fashion, you want to make sure that you minimize the attacker's choices. For example, we already seen this morning that for some implementations, the amount of options you have in order to control small parts of the secure boot implementation can lead to particular threats that can be materialized. Also already mentioned, you want to make sure that you authenticate everything. And it does not only mean you want to authenticate the code that's being executed, but also the data that the secure boot implementation relies on. Because otherwise you might trigger vulnerabilities which you could not trigger if it was properly authenticated. And please remember, you need to authenticate it before you use it and not after, otherwise it's kind of useless. So like we've seen, you don't want to use weak crypto. You want to make software exploitation hard. The clicker is not always working. You want to drop privileges when possible, because often an attacker is after a particular asset, and if this asset, reaching this asset requires particular privileges, by restricting the amount of stages that can access this asset, you decrease the size of the attack surface. Also, what we've seen already in the field, but also the examples that we've shown, that fault injection is a real threat on secure boot implementations, and you see it already happening in the field. And moreover, it's always possible that mistakes slip in, but you want to make sure that you can fix these mistakes if they're in software. And when you do, you want to make sure that attackers cannot roll back to a more vulnerable version in order to exploit the vulnerability that was identified in an older version. So what else you can think of? Well, a mature product has a secure system software development lifecycle. And this is exactly what's important in order to verify the hardness of a secure boot implementation. So you want to think of continuous software review and testing. But more importantly, for the hardware, you want to make sure that you test your hardware. Because it's very difficult to do an analysis of your hardware, so what the impact of a fault injection attack would be on your hardware, from just a paper study. Whereas you can review code by sitting behind your computer. In order to verify the robustness of your hardware, you really need to get your hands dirty and start testing. So to wrap up, together with the presentation that we already seen this morning, but also the examples we gave, secure boot is nowadays often not optimally hardened, and especially if you compare it to the system when it's fully initialized. The typical software exploitation mitigations and other features that are used to make it more difficult to attack a device are actually not implemented during boot. Attack surface of secure boot is much larger than often expected. So one of the examples we've shown that the attack surface actually starts before any code is being executed. And also during this presentation, we gave a few new perspectives on attacking secure boot. And by that, I would like to finalize the presentation. We are very happy to be here, and if there's any time left, we are happy to answer some questions. And otherwise, please approach us. We will be here for the remainder of the event. Thank you very much.